So today we will practice with some example about the chapter 14, the aqueous solution equilibrium on acid and bases. So here you have to know, just 1 minute, guys. In the acid-base reaction, we need to find either the pH of the solution, which of course we will need the concentration of H positive, or maybe even the concentration of OH negative. If we have one of them, we can calculate the pH of that solution. Don't forget, here we have OH, for example, so the concentration of H positive times the concentration of OH negative will equal 1 times 10 to negative 14. And also, don't forget, pH equal minus logarithm the concentration of H positive. Or if we have a basic solution, so POH, we can calculate minus logarithm the concentration of OH negative. Now, in a strong acid or basic solution, look how you will deal with it. Strong acid will be the HA dissociate completely in the presence of water. That's it. HA plus water dissociate completely, approximately 100%, to give you H3O positive, which represent the H plus, and A negative. Now, when it's completely dissociate, what does that mean? If you have 0.5 molar here, water is liquid, we don't wear both concentration of it. The H3O positive or the H plus will be 0.5 because we have just one H. The A negative will be 0.5 because also we have one. Here, you remember the concentration of ion. You will multiply the mole-to-mole ratio between the ion and the compound with the concentration. So if you have, for example, 2H, you will multiply 2 times 0.5. 1H, 1 times 0.5. And depends, like I'm saying 0.5, just assuming the concentration is 0.5. Now, when you have this situation, the pH in this situation will equal minus logarithm the concentration of H plus, which is the 0.5. And you will find the pH of solution. Now let's look for basic solution. If it's strong, let's say we have NaOH. NaOH in the presence of water will give you Na plus and OH minus. So they will dissociate. We will not write it down the OH in the equation here. Sorry, the H2O. So it will dissociate the positive and negative ion. So if I have, for example, 2 molar here NaOH, so this one will be 2 molar here, 2 molar, and here the POH will equal minus logarithm the 2 molar. And you will find the pH, then you will find the pH, because pH pOH equal 14. So that's how we will deal with the strong acid or strong base. It is easy to calculate the pH of the solution because it's easy to find the concentration of H plus or the OH minus. When we have a weak acid solution or weak base solution, In that situation, you have to use the equilibrium constant expression for them because they will not completely dissociate. In uh, let's go to another page. So in the weak acid or weak base, the dissociation is partial. So if I have a weak acid like CH3, COH, it's reacting with water, will be partial dissociation. Now this will give me CH3, COO negative plus H3O positive. In this situation, if I have 0.1 molar here, I cannot say here 0.1 molar, 0.1 molar. This is totally wrong. Why? Because just a little bit of the CH3COH will dissociate. Just a little bit, not total. So what you're gonna do in this situation? If I have 0.1 molar here we need to use, for example, the ice table. Here the initial, here the change, in the equilibrium. So here 0.1 water, we don't care about it. Nothing here. Here will be 0, 0, for example. And the change here, reacting, minus x. The same things what we learned for the ice table is the equilibrium reaction when we talk on the previous chapter. Here it will be positive x, here positive x. Don't forget the coefficient number for each of them. So the change will be x. And at the equilibrium here, 0.1 minus x, here x and x. And then, of course, when you decay equilibrium, to have the product, which is this one and this one, x times x divided by 0.1 minus x. And that will give us x squared divided by 0.1 minus x. And then we will solve the problem to find x. And we will do the same things, the approximation, 0.5%. It's supposed to be this valid, it will be valid if it will be less than 0.5%. And we can use also the quadratic equation to find the x if it's complicated. So we will do, that's what we're going to do when we have weak acid or weak base. Weak base will be exactly the same, but here, this K equilibrium, by the way, we call it Ka, K sub A. And the weak bases will be K sub B. So this is the difference, but also it will be the same types of calculation. Okay, now let's go and practice with some example quickly here. Okay, let's do this example. What is the pH of a human blood in which the concentration of H3O positive ion it is 4.0 times 10 to negative 8 mole per liter? B 0.020 molar HCl. So here, first of all, the pH equal minus regarding the concentration of H3O positive. Now, in A, they already give you the concentration of it. So here, for this one, it will be minus regarding the 4.0 times 10 to negative 8. You will get the pH, or you're gonna be equal. Guys, try to do it, the calculation and your calculator. I will just go without doing the calculation in the calculator. I just show you the numbers and you will just plug it in your calculator to find the answer. Just want to go and practice with more example. Okay, so here you will get the logarithm for this one and you will have it here. Let's see if I have the log in my calculator, because I don't have the calculator with me right now. So here, okay. 4 times, okay, it doesn't have. So as I said, guys, so try to use your calculator to find, excuse me, to find the log for this one. Now, this is for A. Now for B, they need to find the pH of 0.020 molar HCl. So what are you going to do here? Look at here. HCl. You have to remember HCl is a strong acid or weak acid. We have several acids. You have to memorize it as a strong acid, and the other will be dealing with it as a weak acid. HCl is one of the strongest acid. So HCl, because it's a strong acid, when reacting with water, will dissociate completely to give you H3O positive plus Cl negative. And here, because it's a strong acid, 0.020 molar will dissociate to give you 0.020 molar and 0.020 molar. Why it is the same? Because we have one H and one Cl. If you have two H, you will multiply this polarity by 2. If you have two Cl, for example, but that's not the case. We don't have two Cl because hydrogen is always has one positive charge. Okay, so we have the concentration of H3O positive. So we will do the same things what we did previously. Well, pH will equal logarithm d 0.02. Do the math, do it in your calculator, and here you will find the pH what you put for this solution. Okay. And that's what you're gonna do with strong acid, guys, with the strong acid. With the weak acid, we will not do this. The weak acid, we will use the equilibrium expression. And look here, if I have the number, that's cool. We can put it here. So the pH will equal this equation, and the pH for the first solution in A will equal 7.4. And here, the pH, since HCl is a strong acid, the entire 0.020 molar will dissociate. And this is the pH. Okay. Calculate the pH of 0.077 molar NaOH. Okay, so here we have NaOH. So NaOH is a strong base, will dissociate completely to give you Na positive plus OH negative. So here we have 0.077, 0.077 and 0.077. Now, the concentration of H plus or H3O positive will equal what? 1 times 10 to negative 14 divided by concentration of OH minus. Don't forget this, I get it from this equation. H3O positive times the OH negative will give me 1 times 10 to negative 14. So here, I will do this equation. 1 times 10 to negative 14 divided by 0.077, and I will get here what is the concentration of H positive. Now, they are asking for pH. So here, I will use the pH will equal minus logarithm the concentration of H positive. And you will find what is the pH of solution. So do the math and you will look for the pH of the solution. Okay. So the H3O positive will equal 1.3 times 10 to negative 13. Then the pH will equal approximately 13. Okay, now let's go with this example. Calculate the pH and percentage deprotonation of 0.1 molar CH3COH. Given the Ka for acetic acid, that is 1.8 times 10 to negative 5. It's important to be able to write an equation for the reaction. Sometimes it's confusing for us. So look at here. This is the acid. In general, HA plus H2O give us H3O positive plus A negative. A here is the CH3COH and this is the H. And you will deal with it the same way. A negative and this is the CH3COH. Okay, one more thing. Here we have 0.1 molar. Because this is a weak acid, we cannot say 0.1 molar will give me 0.1 molar H3O positive and 0.1 molar here. No, that doesn't work. Why? Because CH3COH is a weak acid. If it's a strong acid, if it was a strong acid, yes, that's fine. But here, it is a weak acid. So it doesn't work. What are you going to do in this situation? We will use a stable. Okay. So initial. Change. And equilibrium. Initial was 0.1 molar. Guys, water here will not be included. Why? Leave it blank. Because it is liquid. And we don't include it in the equilibrium expression. Okay, here 0, 0. The change will be x, but for reacting will be minus x, negative x. For product will be positive. So here, reacting and the product will be x minus x plus x and 1x because I have one product, one reacting, so it will be minus 1x. Don't forget the coefficient. So here minus x and plus x plus x. 0.1 minus x, x. Now, K equilibrium, we need to find the x to be able to calculate the pH. We have the x value, which is the concentration, which represents the concentration of pH plus, so we will be able to calculate the pH of the solution. Now, K equilibrium for acid, we call it K sub A. Okay, for acid, K sub A. For base, K sub B, but the same way, but we are dealing with OH, not acid. Okay, so here, we're going to do the product, so it will be x squared divided by 0.1 minus x. That will give me equilibrium 1.8, 10 to negative 5, equal x squared divided by 0.1 minus x. Do the math, and we will get the x equal. I think I have it here. Let me just show it to you. Yeah. Okay. So look at here. That's what we did. So x plus x plus x. Notice x means the concentration is going away, and plus x means the appearing. Okay. And here, equilibrium equal this, x will equal. Okay, now we have to notice that. Since K equilibrium, when we reach this point, since K equilibrium is 1.8 times 10 to negative 5, which is much less compared to the 0.1 molar, which was the initial, we can ignore the minus x in 0.1 minus x. We will ignore it. But we will ignore it only in the reactant, the minus x. Guys, in this situation, when you're in this situation, you either go and do approximation, like what we're going to do here, or keep the x, especially if the Ka it is large, and use the quadratic equation. Or sometimes we have some issues, some type of question that we can calculate the x mathematically easy. But as I said, here we have to do the approximation, or we can use the quadratic equation if we will keep the x. And be careful, you will do or ignore the x in the reacting, okay? Now, when you will do the approximation, we will have this situation. So we will have Ka equal x squared divided by 0.1, and x will equal this. Do the math, you will find the x equal that one. And that amount represents the H3O positive, which equal also the CH3CO negative. Then we will use the pH equal minus logarithm the concentration of H plus for H3 positive, and that will give us 2.89 as a pH. Since this is less than a pH of 6, ignoring the autopyrolysis of water is valid. Because remember here, the water will dissociate also to give H plus and OH negative. But the dissociation of it is very, very small when you will not affect all when you compare it with the dissociation of the H plus that's coming from the acid. Now, percentage deprotonation will be the amount of X here, which is the X, the H plus, divided by the initial concentration 0.1 times 100 give you 1.3%, which is less than 0.5, less than 5%. So our validation or our approximation here was valid. If the percentage not less than 5%, you guys have to go back and here, you have to go back here and use the quadratic equation to find the X. But it was less, so you are fine. Your approximation is valid. Okay, so to this example. Calculate the pH and percentage deprotonation of 0.22 molar aqueous fluoroacetic acid. Be sure to check any approximation to see whether it's valid or not. The Ka for fluoroacetic, it is 1.4 times 10 to negative 3. So here we will have 5.24. Okay. So we will start also with the ice table. Here 0.22 molar, 0, 0, minus x, minus x, minus x, sorry, plus x, plus x. So here 0.22 molar, minus x, here x, here x. K equilibrium, which is the Ka equal x squared divided by 0.22 minus x. Now, we need to see if we can ignore the x or not. We will compare the Ka with the 0.22 molar. Let's see. We have 0.0014 divided by 0.22. So it is. So here, so look at here, guys. So our approximation, I think, will be valid if we will assume that x sorry guys. Okay, so here 1.4 times 10 to negative 3 will be less than 0.22. Okay, so it is very small because the percentage it will be around okay, let's check. Which means you will probably have to use the quadratic equation. It is larger. So here, what you're gonna do? Oh yeah, 0.014. Actually, here we can use the quadratic. Oh yeah, it will be. It will not be larger actually. Okay, it will be smaller. Okay, guys. So here you can solve, but you do the approximation, guys, like what they did here. So you can do the approximation. Okay, they did the approximation. They found the x. Okay, so they found the x. After they did the approximation, x was 1.8 times 10 to negative 2. Now we will check the percentage for change. Divided the x by 0.22 times 100. It gives me 8%. It's more than 5%. So our approximation not valid. That means we need to go back and use the quadratic equation. Use the quadratic equation to find the x value. Okay. Let's see this slide here. So here we have the K equilibrium will equal the x squared divided by 0.22 minus x. This will go to x squared plus 1.4 times 10 to negative 3 x minus x minus 3.1 and 10 to negative 4. Solving for x using Microsoft Mathematics. You can use it to find the x to deal with this quadratic equation. Okay, so here x will give us as a two value, either x 0.017 or point okay 0.017, or it will give you also maybe a negative value. Ignore the negative value. So here an x in a quadratic equation, x could be positive and negative. Ignore the negative value of x. Just use the positive. So it will be 0.017. So here, the acetic acid, sorry, the chloroacetic acid was 0.22 minus 0.017, gives us approximately 0.02. The H3O plus, which represent the X, will be 0.017 and will represent also the ion concentration. Now the pH will equal minus to than the concentration of H plus. This is the concentration of H plus. Okay, so that's what we have, 1.77. And percentage deprotonation, it is the X, always X divided by the concentration of, what is it here? It is X divided by the concentration of initial concentration of acid. And of course, times 100. Okay, that's 7.7%. Okay, let's go and practice with another example. And I know, guys, like when you have to use the quadratic equation, it's a little bit challenging. You have to do a lot of math on it, but that's what you have to do. It. We have to deal with it if it's not valid for approximation. You have to use the quadratic equation. The quadratic equation, I will give it to you in the exam to use it, but also you still like you have to do more math to get the X. Okay, let's look to this equation. Example. Here find K given pH. Okay, the pH of 0.01 molar aqueous solution of manolic acid. Is 2.95. What is the Ka of manolic acid? They are asking for Ka, the equilibrium constant. This is the manolic acid with the water, because H3O positive and the negative ion. We've calculated the Ks like this in the previous chapter, okay, which is when we talk about the K equilibrium. So we will use the ice table. So here, ice table. What do we have? Initial here, 0.01 molar, 0, 0, minus X, plus X, plus X. Equilibrium will be 0.01 minus X, X, X. Okay, now K equilibrium, which is Ka, will equal what? The X squared divided by 0.01 minus X. Now, they are asking for the K equilibrium constant of the acid, the Ka, dissociation constant for the acid. So here, we need to find the X here? Look at here. The X represent what? Represent the H3O positive. So here, concentration of H3O positive, which equals the X, will equal what? Will equal 10 to negative the pH. 10 to the negative to the power negative the pH. That's how you will calculate the concentration of H positive. It is the antelope. They give you the pH. So here it will be 10 to negative 2.95. Look at the concentration of H3O positive, which is the X. And here, whatever it is, we'll substitute it in this equation to find the Ka. Now let's look in the second slide. So they have a number. Okay, so look at here. They found the pH, sorry, the concentration of H positive. It was 0.001. So here the X will be like this. This X will be 0.01. This one, after you subtract the X, will be this. Now substitute it in the Ka equation. And that's what we will have. So we will have Ka equal X squared, which is this one, X. This X squared was, and here the 0.01 minus X. Substitute it here, and you will get the value of Ka for that acid. Okay. Let's go with this example. Calculate the pH and percentage protonation of 0.2 molar aqueous solution of methylamine, CH3 and H2. The case of B of methylamine is 3.6 times 10 to negative 4. Guys, for the bases, the weak bases, it is the same idea of the calculation for the Ka, but here we will use K sub B and OH negative. We will calculate the concentration of OH negative instead of Ka and concentration of H3O positive. But it is the same way, same idea. The approximation, the quadratic equation, the same way. Now look at here. So for this reaction, we will start with the ice table. So ice table. So here 0.2 molar water, ignore it. Here 0, 0, minus X, plus X, plus X. Here will be 0.2 minus X and XX here. Now here they are asking for the calculated the pH. Now here, if I have the X, I will be able to calculate the pOH. Or if I have the X, I will be able to calculate the H3O positive concentration, which is 1 times 10 to negative 14 divided by the OH negative. Then we will calculate the pH. Anyway, first of all, we need to find the X. K equilibrium will equal X squared divided by 0.2 minus X. Now the K equilibrium is 3.6 times 10 to negative 4. And when you will multiply this, by 100, I think it is less than 0.20 molar. So it will be, we can do approximation. It's valid for the approximation. And as I said, guys, even if you're not sure if it's valid or not, do the approximation and figure out the 5% and compare it. Compare the XA, so it will be the X divided by initial concentration times 100. If that one less than 5%, your approximation valid. Larger, your approximation not valid. You have to use the quadratic equation. Okay, so let's go and look here. Okay, so here what we have, that's the ice table. Now we will substitute it in this equation, and we will do our approximation. So K sub B, which equals this amount, equal X squared divided by 0.2. X will equal this amount. And don't forget, this is not, in this situation, when we have weak bases, be careful guys, this is not the H plus, this is the OH negative. So here, you will find the POH, which is minus regarding the concentration of OH negative, which equal here 2.07. And here, later, we will find the pH, which is 14 minus 2.07, and that will give you 11.9 approximately. Just to check the percentage deprotonation, which will equal the X divided by the initial times 100, equal 4.3%, which is less than 5%, which is our valid, our approximation is valid. So that's how we will deal with this type of calculation, if it's weak acid or weak bases, and we already talked about strong acid or strong bases. To find the concentration of H plus, OH negative, or the pH or the POH, whatever they are asking.